Now, mathematically, we can convert between our geodetic coordinates and our ECEF coordinates. And here's the mathematical equations to do so for our X, Y, and Z values, given a particular specified latitude, longitude, and height. And this will give us our ECEF data in meters in our X, Y, and Z values. Now we need to calculate our N value for this. And for our N value, we use that semi-major value A, which is specified in our WGS84 coordinate system. Now I should say that converting in the opposite direction is harder. We're not actually going to do it within this course. It's beyond the scope of what we need to do in this course. But I've shown you above, if you follow those equations up there, they'll allow you to convert between a geodetic coordinate in latitude and longitude and altitude or height and our ECEF point. We have one other coordinate system that's of interest, which is the east-north-up system. Basically, in the east-north-up system, we project a plane onto our ellipsoid. And the center of that plane is the center of where that plane touches the ellipsoid. And that will be 0.000 in our ENU, or our east-north-up position. Now that plane will sit on the surface of our ellipsoid, and we specify how far east we have from that center point, that point 000. So if we go in an east direction, it will be a positive value. If we go in a west direction, it will be a negative value. We specify how far north we go from that. So if we go north, like north 2 kilometers, it's a positive value. If we go south, it's a negative value. And then we specify how far up we go off that ellipsoid plane. Now I should mention here, we're considering this as a plane. So we're not considering the curvature of the Earth, so we can only use this for smaller areas. We've got other things like a UTM transformation, which is also beyond the scope of this course, that we can use if we're trying to use something like this in a larger surface area. Now, how do we compute this out? Now, here's how we compute this out. We've got this matrix down here, which allows us to specify our points in terms of X, Y, and Z. We'll have our reference ECEF position, which is the position at the center of our ENU plane that we're dealing with. And then we'll have a target ECEF position, which is the position that we want to specify with respect to that center point that we were dealing with before. Our X, Y, and Z is our east, north, up units. And our sigma and lambda specify our latitude and longitude respectively. So one place we might use this more naturally is somewhere like an air traffic control tower, where we're not so much interested in what's our exact latitude and what's that plane's latitude and what's their longitude and things like that. But if we think about what's our location and how many kilometers or meters are they north of us and how many meters or kilometers are they east of us and how many kilometers or meters are they in terms of their altitude from our altitude. And so that sort of frame of reference makes sense if we're looking at this air traffic control tower or an airport or something like that is at the center, and that might be at our center reference point in our reference frame and plane that we're dealing with, and where are other objects with reference to that point. On a construction site, we might have some sort of a control point that's our datum point, and we measure everything from that point. And so it might be 500 meters east and 10 meters south, which is a negative, so minus 10 meters, and then a certain altitude, a certain distance in terms of elevation up from that particular datum point. So our first example here, we're going from our geodetic to our ECEF point. And so we've got our latitude and longitude and height specified, which is our geodetic data. And we want to convert that to an ECEF point, which remember is going to be a Cartesian value in X, Y, and Z. So we use our equations that we had previously with X, Y, and Z. We're going to assume that we're using WGS84, and using WGS84 and our A value for the semi-major axis and our eccentricity squared, we can work out what our N value is going to be. And then we can compute. We then need to represent our latitude and longitude in terms of radians. And once we've converted them to radians, we can then work out what our X, Y, and Z values will be, which we've done there. And they come out in meters. Obviously, we can convert them to kilometers from there. Next thing we can do, in our next example, we can look at going from ECEF to ENU, our east-north up units. Here we specify both a reference point, which is going to be the center of our ENU plane that we're dealing with, and the actual point that we're interested in with a latitude, longitude, and height. So we can multiply out our matrices there to work out what our values or our equations for X, Y, and Z in the ENU are going to be. We can then substitute all our values in and using radians for each of these values. And that will give us an X, Y, and Z value of the point that we're interested in with reference to that reference point, which is, remember, at the center of our ENU plane. One little check that we can do is look at the Euclidean distance between our center reference point value and the point that we're dealing with. And we can compute this two different ways, one in the ECEF and one in the ENU, and they should both agree because they're equivalent reference units to each other. And in this case, they do.